In the previous two lectures on calculus of residues, we have learnt about the calculation of residues in different situations. Actually, we have learnt the different techniques to solve the problems on calculation of residues calculation. Now today we are going to know how the numerical problems based on residue calculations can be solved by using those techniques. So let us start with the first problem. The problem actually states that classify the singularities and calculate residues for f of z equal to 1 over z square plus a square whole square where a is greater than 0. To solve this problem, first of all we will find the singular points, or you can say the poles of the given function f of z. And you know, for finding the poles of the function f of z, we actually equate to 0 the denominator of the given function f of z. And for this, first of all, we simplify the given function f of z. You can see f of z is equal to 1 over z square plus a square whole square. And we can write this in this way. This is 1 over z square minus ia whole square and whole to the power 2. Since you can see I square is minus 1, so that minus and this minus will be plus and the result will remain same. Now applying the formula a square minus b square, we can write this expression as 1 over 1 minus z minus ia whole square into z plus ia whole square. So the denominator is z minus ia whole square into z plus ia whole square. And as you know, whenever we have to find the singular points or the poles of this function f of z, we will simply equate the denominator to 0. So let us equate it to 0. So taking z plus ia whole square into z minus ia whole square equal to 0, we can see that there will be two solutions of this equation. First one is z plus ia equal to 0, which gives us z equal to minus ia. And the second will be z minus ia equal to 0, and it gives us z equal to ia. So you can see that there are two poles. First one is z equal to minus ia and another is z equal to plus ia. And as the power on the factor determining the poles of this function is 2, so you know this power actually denotes the order of the pole. So these poles are of second order. Thus you can see that the given function f of z has two poles, z not equal to plus ia and z not equal to minus ia, and order of the pole is 2. Since order of the pole is 2, so we can actually apply the formula to find the residues which we have learnt in the previous lecture. So let us first of all find the residue when z not equal to ia. It means the pole is of second order and it is at z equal to ia. And as you know, for in general for an mth order pole, what is residue? You know a minus 1 is the residue of the function, and for mth order pole it is given as 1 over factorial m minus 1 into limit z tends to z naught, where z naught denotes the pole, dm minus 1 over dzm minus 1 operated on z minus z naught to the power m into f of z. As you have seen that in this problem the order of the pole is 2, so here m will be equal to 2. So let us put the value of m, that is equal to 2, and the value of f of z, which is given in this problem. and after simplification we will get the residue of this function at its pole z equal to ia. So what will be our result? So the residue a minus 1 will be simply equal to 1 over 2 minus 1 factorial into limit z tending towards ia d2 minus 1 over dz 2 minus 1 operated on z minus ia whole square into f of z is what? F of z is 1 over z minus ia whole square into z plus ia whole square. So you can see this z minus ia whole square will cancel out, and this will be simply, as you can see, this 2 minus 1 is 1 and factorial 1 is 1. So this is simply 1, and our result is limit z tends to ia d by dz operated on 1 over z plus ia whole square. Now you simply differentiate this 1 over z plus ia whole square. What will be this? This will be simply minus 2 over z plus ia whole cube. Now we will put the limiting value of z, which is in fact ia. So let us put ia at the place of z, and this will be what? This will be minus 2 over ia plus ia will be 2ia, and so this is 2 over 2ia whole cube, and this will be actually equal to 1 over 4ia cube. So this is the residue of this given function f of z at its pole z equal to ia. In fact, in similar manner, you can find the residue of this function at its another pole, which is z equal to minus ia. I am not solving it completely, but it is given to you as a homework. You can see and follow the same steps as I have followed in the previous problem, and so you will get simply that residue will be a minus 1 equal to minus 1 over 4ia cube. So you have seen how we can find the residue of the function when the pole is of an arbitrary order. Now let us take another important example. In this example, the given function f of z is equal to z to the power minus k over z plus 1, and here the value of k lies between 0 and 1. It means what? It means k is actually fractional and its value is positive but fractional, like 1 over 2, 1 over 3, 1 over 5. It means it is smaller than 1 and greater than 0. So this problem is somewhat different from the first problem, but technique will be same. You can see here f of z is equal to z to the power minus k over z plus 1, and this may be written as 1 over z to the power k into z plus 1. Now again, to find the singularity of this function f of z, what we will do? We will simply equate the denominator to 0. So let us take z to the power k into z plus 1 equal to 0. And so this function will have again two solutions. We can take z plus 1 equal to 0, and if z plus 1 is 0, what is z? Z will be simply minus 1. And again you can see this z to the power k equal to 0. Since k is a number lying between 0 and 1, so this will be valid only when we can take z equal to 0. Now you can see that the value of k is actually fractional, and so it represents a special type of singularity. In fact, this is actually fourth type of singularity, and this singularity is known as branch point. and you can't say its order. It is not an order determining singularity or pole, but it is a special type of singularity which is called branch point. So singularity will be determined actually by the another solution of that equation, and you can see this fz has a simple pole at z0 equal to -1 and branch point at z equal to 0. Why I have told you that this is a simple pole? Because you can see the factor z plus 1 contains power 1, and so the order of the pole will be 1. So since it is a simple pole, so you can apply the formula for the simple pole for finding the residue of this function. And you know, in case of a simple pole, what is residue? Residue a minus 1 is simply equal to limit z tends to z0 operated on z minus z0 into f of z. Now, since z0 is equal to -1 and f of z is equal to 1 over z to the power k into z plus 1. So what will be our result? Our result will be a minus 1 equal to limit z tends to -1 z plus 1 into 1 over z to the power k into z plus 1. So this z plus 1 will cancel out, and our result is simply a minus 1 equal to limit z tends to -1 1 over z to the power k. Now let us put the limiting value of z. This is actually -1, so this will be simply 1 over -1 to the power k, and you know this 1 over -1 to the power k may be written as e to the power minus ik pi. You can verify by finding the value of e to the power minus ik pi. As you can see here, that e to the power minus ik pi will be equal to what? This will be actually cos k pi minus I sin k pi, and this is actually equal to 1 over minus 1 to the power k. Now we will take another important example to for finding the residue of a function f of z equal to a of z over sine of z, where a of z is an analytic function and contains no zero. It means a of z is never 0. For any value of z, it is not 0. So you can see this problem is somewhat different, but we have learned the technique to find the residue of such problems in the previous lecture. You can see in this problem, the form of function f of z is actually equal to in the form of g of z over h of z. In fact, when I was dealing with the techniques to find the residue of a given function, we have used this symbol f of z equal to g of z by h of z, where g of z and h of z both are analytic function. We have learned it in the technique while studying the calculation of residues. So if we take sin z equal to 0, sin z equal to 0, then you can see this z will be what? This will be simply plus minus n pi. Actually, this is the general value of z which will satisfy sin z equal to 0. And if you say that z equal to plus minus n pi, the value of n are what? N will be 0, 1, 2, 3 and so on. Now consider that this h of z is equal to sin z. If we consider that h of z equal to sin z, then what will be h prime of z? When you say h prime of z, it means the dh of z by dz. That is, this is the first order derivative of h of z, and since h of z is sin z, so this derivative will be cos z. Now you can see when we take z equal to plus minus n pi, in that condition sine of z, and sine of z will be written as h of plus minus n pi, that is sine of plus minus n pi, and this will be simply 0. But its derivative, that is h prime of plus minus n pi, which will be cos plus minus n pi, and you know cos minus theta is equal to simply cos theta, so we will write it as simply cos n pi, and this cos n pi is not 0, but this will be actually equal to minus 1 to the power n. It means its value will be, when we take n equal to 0, this will be 1. When we will take n equal to 1, this will be minus 1. When we will take n equal to 2, this will be 1. So alternately, the value of cos n pi is equal to 1, minus 1, again 1, again minus 1, and so on. So we can see that although h of z is 0, but h dash of z is not 0. So in this condition, you have learnt in the technique in previous lecture that this function f of z has a simple pole at this point z naught equal to plus minus n pi. So now the type of the singularity and its pole has been determined. The singularity is of what type? It is just a simple pole, and at what point? This is at the point plus minus n pi. So now we can apply the formula which we have learned to solve such types of problem. We know in this condition the residue of the function f of z at its pole z naught equal to plus minus n pi is given as a minus equal to g of z naught over h prime of z naught. Actually here I have mentioned the formula which we have used in the development of the theory to calculate the residue. But in this problem you can see this g of z naught will be simply a of z naught. So what will be this? This will be a of z naught over h prime of z naught. But this z naught is plus minus n pi, so we will write it a of plus minus n pi over, and you have seen that this z h prime is simply cosine function, and so this will be cos of n pi, and cos of n pi is equal to minus 1 to the power n. So the residue of this function at its simple pole at plus minus n pi is what? This will be a of plus minus n pi over minus 1 to the power n. So this is another type of problem which we have learnt in the previous lecture. Now let us take another example which is also very important, and it is also something different from the problem which we have dealt now. So the problem says the function f of z is equal to sin z over z to the power 4, and we have to calculate the residue of this function at its poles. So you can see here, if we take z equal to 0, then sin z will be 0 and z to the power 4 will be also 0. So this function in this condition will be of the form 0 over 0, which is in fact indeterminate. So no direct calculation of the singular point can be used, and the order of the pole are not possible to determine directly by the set pattern or set formula. So I have told you while dealing with the techniques of calculation of residues, that in this condition we simply expand the transcendental function. Here the transcendental function is what? This is sin z. So we will simply expand the transcendental function sin z in this case, and then you will see the series will become a Lorentz series, and from that Lorentz series we will find the coefficient of z minus z naught to the power minus 1, which is a minus 1, and that is called residue. You know sin z equal to what? This is actually z minus z cube over factorial 3 plus z to the power 5 by factorial 5 minus z to the power 7 by factorial 7 plus so on, and whole divided by z to the power 4. Now let us divide each term of the numerator by this factor z to the power 4. So what will be the result? This will be simply z by z to the power 4, which is 1 over z cube, minus z cube by factorial 3 into z4, that will be 1 over factorial 3z, and the other terms are z to the power z divided by factorial 5 minus z cube by factorial 7. So you can see actually this series may be arranged in this particular manner. In fact, inside the first bracket we have taken the terms containing the positive powers on z, and in the second bracket we have considered the terms containing the negative powers of z. So you can see this series, in this series actually the positive powers are in the form of z minus z naught to the power 1, z minus z naught to the power 2, and in the second part of the series containing the negative powers on z, this is actually of the form of z minus z naught to the power minus 1, z minus z naught to the power minus 2, and so on. And so you can say this is simply a Lorentz series. But this Lorentz series is about what point? You can see, as instead of z minus z naught, there is simply z. It means what? It means z naught is equal to 0. And what is this z naught? Z naught is actually the isolated singular point of this function f of z. So you can say that this is a Lorentz expansion for f of z about the point z naught equal to 0. And as you know that this z equal to 0 is content, z equal to 0 is content in this series, and as you can see that in the denominator the highest power is actually z to the power 3, and so the order of this pole is actually 3. So this is the type of singularity, and we will not use the formula for finding the residue for mth order pole here, because this is something different problem, and I have told you while dealing with the technique to find the residue that in this condition, when once we find the Lorentz expansion, we simply see what is the coefficient of the term containing the factor z minus z naught to the power minus 1, and that gives actually a minus 1. So in this problem you can see in principal part of the Lorentz series, the coefficient of z to the power minus 1 is minus 1 over factorial 3, and in accordance with the definition of residue, you know this coefficient minus 1 over factorial 3 actually represents a minus 1, that is residue of this function. So you can say residue of this function will be a minus 1 equal to 1 over a minus 1 equal to minus 1 over factorial 3. So you have seen this is not the problem which can be solved by direct applying the formula to find the residue. Now let us take another important example. Here the function f of z is equal to z into e to the power 1 over z, and we have to find residue of this f of z. Again, you can see this problem cannot be solved directly by applying any established formula. So we will do the same technique as in the fourth problem. We will simply expand the transcendental function e to the power 1 over z, and then again for finding the residue we will find the coefficient of z to minus z naught to the power minus 1. So let us expand this function. F of z is equal to z, and this e to the power 1 over z will be what? This is 1 plus 1 over z plus 1 over factorial 2 into 1 over z square plus 1 over factorial 3 into 1 over z cube. This is simply expansion of e to the power x. Here x is equal to 1 over z. So what will be this? This will be simply z plus 1 plus 1 over factorial 2 into 1 over z plus 1 over factorial 3 into 1 over z square and plus so on. And you can write this as z plus 1 plus 1 over factorial 2 z to the power minus 1 plus 1 over factorial 3 z to the power minus 2 and plus 1. So you can see this is just a Lorentz series about z equal to 0. So this is Lorentz series about z naught equal to 0. And therefore what will be the residue? Residue is simply the coefficient of this term z to the power minus 1. So the residue is just the coefficient of z to the power minus 1, and that is what? That is 1 over factorial 2. So the residue of f of z is simply the coefficient of z to the power minus 1, and therefore this is a minus 1 equal to 1 over factorial 2, and 1 over factorial 2 is simply 2. So this will be the residue